Okay, now we're going to look at portfolios and how we represent them. In market risk, we like to use portfolio weights, but you also have to understand the distinction between the holding and the weight. So that's what this simple video is about. And I'm going to be referring to Excel workbook that's in Unit 3, Topic 3. Actually, I won't go through it in this video, but I will in the next one. This looks at a portfolio of two shares, Amazon and Tesla, in the S&P 500 index. And I already showed you in a previous video this graph of the S&P 500 index that goes from 3,500 up to 5,500. That's the black line. And the Amazon stock, which has not been this price, the share price has not changed too much. Tesla also being rather volatile, more so than Amazon. Okay, so the holding of an asset in a portfolio is just the number of units, the number of shares of a stock, or the number of bonds that you hold. But the weight is the proportion of the portfolio value that is invested in that asset. Now, in practice, it's very easy not to rebalance the portfolio at all, and so the holdings are held constant. But that means that the portfolio weights change every time the price of any asset changes because of the definition of the weight. The weight is the proportion of the whole portfolio value invested in that asset. So if the price of one asset changes, then the whole portfolio value changes. And that means the weight of every asset changes. So let's have a simple example related to the spreadsheet. Suppose you've got 100 shares of Amazon and 200 shares of Tesla, and that the price of Amazon is $20 and the price of Tesla is $25. Then the value of the portfolio is 100 times 20 for Amazon plus 200 times 25 for Tesla, which is 7,000. And so the weights are 2,000 for the Amazon over 7,000, that's 28.6, and 5,000 over 7,000 for Tesla, which is 71.4. And then if either stock price changes from 20 or 25, then the value changes, and that means that the whole weight of every asset changes. Okay, so market risk calculations are based on historical returns, and if you just assume that what you've got at the moment was not actually rebalanced during the historical period, probably it was, but if you just say that, okay, I'm just going to recreate a hypothetical value based on the holdings that they are now, you can do that. But when we calculate market risk, it's actually much more convenient to just assume that the weights are as they are now for the whole historical period. So you have to reconstruct your artificial returns based on that assumption. Okay, the reason we do that is because you can get a much more simple formula for the variance of the portfolio, and that is the sort of main input into market risk. So how do we calculate portfolio weights? What do they look like? So suppose we've just got long positions, just to keep things simple, and you've got n assets with returns R1, R2, R3, Rn, okay? And it's a linear portfolio. In other words, the portfolio is just a linear function of these positions. And in particular, you can define it in terms of the weights on each asset, the proportion of the total amount invested in that asset. So let's make the weights vector W1, W2, W3, etc. And for a fully funded long-only portfolio where you're not borrowing anything, you haven't got to take into account any payments on your discount bond or whatever it is you've used, then just the sum of the weights is 1. So if I've got like 5 million and I invest 1.5 in asset 1 and 3.5 in asset 2, portfolio weights are 1.5 over 5, which is 0.3, and 3.5 over 5, which is 0.7. I'm sure you understand that's simple. Now, suppose you've got let's forget foreign exchange, so it's just a domestic stock portfolio. And the reason we call it a linear portfolio is that its return can be written as a linear function of the individual ordinary returns on each asset. In other words, we can write the return on the portfolio RP, R sub P, as the sum of WI times RI. It's the weighted sum of the ordinary returns, not the log returns, but the realized returns. And we can also write this summation formula as W dot R or W prime R. I'm choosing to write it in this slide as W prime, the transpose. So that W transpose is a row vector because everything is column vectors unless otherwise stated. So W is a column vector of portfolio weight. So W prime is a row vector. R is a column vector of the realized returns on these stocks. And so the dot product, or W prime R, is the same thing. It's just the sum of the weight times the return. And that holds for actual returns, but not for log returns. It doesn't just apply to observed returns. You can have a similar relationship for expected returns as well. And I'm sure you've seen this before, that the expected return on a portfolio is just a weighted sum of the expected return on each asset. So, for example, you've got a portfolio P with $1 million invested in asset 1 and $4 million invested in asset 2. If asset 1 returns 10% and asset 2 returns 5%, what's the return on the portfolio? So your weights are 1/5 because the total is 1 million plus 4 million. It's 5 million invested. That's 0.2 in asset 1 and 0.8 in asset 2. The returns are 10% and 5%. That's what you can see here. And so the return on the portfolio is W prime, which is 0.2, 0.8, no prime, times R, which is 0.1, 0.05 prime, which is 0.2 times 0.1 plus 0.8 times 0.5 using matrix multiplication. So the portfolio return is 6%. So that's it for this nice short video. And I'll see you in the last video of